either inside the atmosphere or outside of the atmosphere, you don't care about. This light is perceived by the eye. We discussed today about the eye, is filtered by that curve, which is the V of lambda. It's a standardized filter. And then the flux, the luminous flux, is the convolution between the spectrum and the filter. Okay? And the 683 in the front has been calculated, as I showed you yesterday, yes. No, this is for daytime. We will, yes, in this session, I will speak about the human vision, and we'll see that the human vision change is dynamic. Okay, this is for the standard one for daylight or for photopic vision. Okay. Okay. I think that everything that the computer cut it, well, he cut another one, but was not very important. This one was the most important. Okay. Then I will suggest to start. Maybe some others will arrive. And this morning, at the beginning of the morning, I will speak you about the human vision. Sorry. My allergy is starting again. That means I accommodate to the local climate and local pollens, and the allergy is coming back. Well, at this first sequence today, we'll speak about human vision and our visual system. You understood that is very important for lighting because all units, everything is based on how we see the light. I will show you here different information about the human eye, and also I will show you some, just let me close this small window here. Okay. Well, first of all, if we take our eye and we look it closely, it's very similar to a very simple optical system. In fact, you have a small hole, you have an object, and the light passing through the small hole will create an image plus or minus well precise in a given distance from the object. Okay, that was a principle that is known since Renaissance times. We're speaking about 15th century. Okay, and in fact that has been used by painters and artists to paint landscapes. We call that the camera obscura. In Latin, what is camera obscura? It's a big box. You have an object that is in principle in infinity, very far, because you don't have any any optical system here. Just a small hole, and behind you can see the image of the object inverted, projected in the screen. And the artist was making the sketch of or the design, if you like, of the landscape, and then after that he puts the color in the right place. Our eye is exactly the same thing. When you see the cyclist, the eye passes through the iris. The iris size can change. We discuss about that, but this is the small hole, and the image is then focused and formed on the front of the eye, which is the depth of the eye, which is the retina. Okay, here is not flat, it's incurvated, but what is important here is that you see the cyclist in the right position, but in reality the cyclist image is formed in the opposite position in your eye. It's not the eye that changes the position of the object. And I will show you an example. Who is this? Who is that person? Margaret Thatcher. Okay? Here you know here. Now if I show to my students, I have to put Madonna because they don't recognize Thatcher is very old stuff. But here you see the image of Thatcher inverted, and you need a given time to put it in the right position. Your brain needs to do that. And if I show you now the two images, it will turn. That one, with the eyes and the mouth inverted, is there. Let's go back. Is that one? But when you look at the image like that, you focus all your attention, who is that? And once you find you are happy, you forget all the details. And you will see this is something very, very interesting, which is closely linked to how our civilization start express by writing words and things and ideas. Let's continue. A little bit more about the optics of our eye. The transparent part of the eye, called the cornea, has a transmission, goes from 1,400 nanometers. This is medium infrared up to 300 nanometers. That means the transmission is going up to UVA. Okay, but remember, the light is defined between 780 and 360 nanometers. That means no infrared at all, no UV, because both can be harmful for our eye. And in fact, as you will see, what is cutting finally the transmission of the eye is not the cornea, is not the transparent part, but this is the crystalline lens, the lens that we have behind the iris and serve to focus our attention to a given distance. This part of the eye cuts the UV and infrared part in order to protect the eye against aggressions. You know, in ancient times, sometimes they condemn people to become blind, and they put a red sword, a very hot sword, in the front of the eyes. In principle, they don't that. It was not. The idea was not to touch the eyes. Could be, but not that. But the infrared radiation from the sword, in fact, burn only the crystalline, and the crystalline becomes completely no more transparent, and you cannot see anything. If at that time we could operate people like today for a cataract, get out the crystalline and put a plastic part as a thing inside, the remaining part of the eye is protected. Okay? Same thing also, UV radiation is very harmful for the retina, and when we make today crystalline operation against, we get out the crystalline and we put a plastic part to replace in the case of some problems with the eye. We select the plastics that they have almost the same transmittance, and they cut UV. Okay. Concerning the size of the iris size for humans change in average between 2 millimeters and say 8 millimeters. 8 millimeters where we are in dark space outside without moonlight, without electrical light or fire, okay? And when we are in a very strong lighting conditions, like today, for example, outside, or if you are in a beach with white sand at noon, then your iris is shrinked in order to against quantity of light penetrating the eye. Okay, this is a automatic protection mechanism. Something happened with that. Okay, it works. This is automatic. It depends on the luminance that you have on the top here is the luminance. When you are outside, you have 10,000 candelas per square meter or 1,000 candelas per square meter, and when you are in the dark, you have 1/1,000 candelas per square meter. We can see in a very large domain. You will see even, we can see more than that. There is also another mechanism that is changing the size of the iris. Our brain can ask to the eye to switch, to increase the size of the iris in order to collect more information from something that can be considered as interesting for the brain. For example, when you are in the market and you look different products, when you see something that you like, your iris will increase in size in order to collect more light. And this principle was known by Chinese merchants at the beginning of our era, when they came in contact with Europeans and things like that. And in fact, Chinese merchants, they look always the people in the eyes, and they have enough training by experience to see variations, and then they can know that is more interesting for me than that. Then we can change the negotiation margin. Okay, this is very interesting. It's not only automatic. It's not only a reflex, the size of the pupil, but it's also of the iris. Is also something that is controlled by the brain. And the best example also that you have is the cat's eye. You know the cat eye, when you have enough light, is very the opening, the aperture is very small, and when you are in a dark, it opens. And but not only look carefully a cat or even bigger cat, when they start attacking, immediately the iris is opening to leave more light to penetrate in the eye. And also the cat eyes has another additional functionality. You see the cat eyes in the dark, you see that it's green, it's reflecting the light, because in fact the light penetrates in the eye, and behind the retina there is a reflecting layer, and the eye passes a second time from the retina and amplifies the image. That's because cats and dogs and other animals can see much better in the dark than us. We don't have really this functionality. Okay, now you understand the different parts of the eye. What are visual fields? What we see? What is the space that we can see? And here you have a first illustration. We can dissociate our visual field in horizontal and vertical. Okay, horizontal, an adult, and this is very important, with a correct vision field, can see almost in 180 degrees in horizontal. Here, if I don't move my eyes, I adjust my hands. Here I don't see anymore that is my field is here. Here I don't see that, my field is here. Okay, you see almost 180 degrees. Vertically is more difficult to do it. We have a little bit smaller vertical field due to the nose and all the parts of our face. There is it again, and here you have some additional information. If you take that in 2D, of course you have 180 degrees in horizontal, 140 in vertical, but in reality, if I put my hands here, I am in the limits. If I close that eye, I don't see anymore that hand. If I close that eye, I don't see that one. If I close that one, now I see it. If I close that one, now I see it. This is almost 120 degrees, is that we call the binocular vision field. And the fact that we have two eyes, which is a little bit in different positions, following to the axis of our face, we can appreciate the depth. if I have an object outside of my stereoscopic binocular, I have to turn my eyes to look where is the object. If the object is here, I can lock you, no problem. I look to you, I can find the object because my brain can appreciate the distance. Okay? What I say here is very important. It will be used then at the end of our teaching this week to explain you the ergonomics, how to light up objects and how also to put the objects in your space. This is very important, and it is in interaction with the light. Then you have also that we call the central vision, which is just in the same line with the vision, which is the place that you have the most precise vision, and in the place that you see the most of the colors. We will discuss about that. And then you have the central vision, and then you have the other circle around 30 degrees. 30 degrees in 20 centimeters is the size of a book. And if you take a normal book and you have it at reading distance, you don't need to move your head to read. You just move your eyes. And that means you have less fatigue to your head. Now, if you take a big book, you have to move your head. That means, since very old times, somehow we knew that property of our vision, and we adjust the size of the object to be visible at once at the right distance. However, the visual field we discuss here change with age. Change, of course, if you have any brain or neurodegenerative diseases, but change also with speed of motion. Normally, I told you it aligns with age. There is, look, a baby, a newborn baby, see almost in 30 degrees, something like that, in front of him. You know very well that when you go to see a small baby and you call him or her, what the baby is doing is always search where is coming the voice. Even if you are almost in the front of his head, don't forget that he doesn't see the same way than you, and you have to wait up to 20 years, 18 to 20 years, to fix the size of your visual field to 180 degrees. That means the day that you have to eliminate primary schools, you have to take into account that the kids, they don't see the same way than the teacher. And how you will eliminate the space, you need to take into account that constraint. Once you have your visual field fixed, doesn't change anymore with the age. Doesn't shrinking when you become more aged, but if you have some problems like macular degeneration due to age, the MLA, in that case, yes, you may lost the central field, and this is very problematic because the central part of your eye is the more sensitive. Okay. Second thing, the field changes with the speed. In fact, a human being is designed by I don't know who to move with a speed of a couple of kilometers an hour, up to 7 kilometers an hour if you are in flat. And the problem is that the photoreceptors, we speak about that, they are not distributed to the same manner inside the retina. The central part of the eye has the photoreceptor that respond more rapidly than the peripheral part of the eye. That means when you move with a normal speed, you have both central and peripheric vision working, and you can see very well what happened in few meters from you. The idea is not to look your feet, but look in the front of you to avoid any obstacle or any danger. Okay. Now, when you take your car, you are moving in the highway. I don't know what is the speed limits here in India. in my country is 130 kilometers hour. 130 kilometers hour is approximately 2 kilometers per minute. Sorry, yes, 2 kilometers per minute, exactly that. And what happened when you look for your destination? You have to see the panel that shows you the exit that you are looking is here, and you have to see it at least few minutes before exiting, at least 1 minute before that. The problem is at 130 kilometers hour, due to the thing that the peripheral part of your eye has not time to refresh the information, only the central part can do it. You see in a cone of 30 degrees, and you see only in the front of you. That means you have to put the panel for the exit in 2 kilometers distance on the top of the lane. Otherwise, you don't see it. And to be visible at 2 kilometers of distance, the panel size shall be something like 20 square meters. 20 square meters. In France, the student dorms is 9 square meters, is the equivalent of 2 student dorms. Well, when I explain that to the students, oh wow, it's really big, and there is a reason. Now, if you are flying, it's completely different. I had a dream to see a firework from above. And one day, flying to US, I flown above Ireland during St. Patrick's Day. And it was fireworks everywhere. Well, I see them, and I was completely deceived. Why? Because you see frozen things. You don't see the development of the firework. You don't see the explosion. You see frozen because looking that you are moving with 900 kilometers hour, even the central part of your eye doesn't have the time to refresh the information that happens in a few hundred of milliseconds, which is all the development and the explosion of the firework. This is very interesting. Same thing also, if you take an electric train and you have the pillars that are getting the current to the train, if you are sitting, you don't see anymore the pillars passing. You have to turn your hand and say there are pillars there, and then they appear, because you force your brain to observe them. This is excellent because if we play with our visual capacities, we can make things visible and things invisible. And if we add lighting, this can completely change the way that we perceive our world. Our vision is a measure what we call the visual acuity. The visual acuity, when you go to the ophthalmologist, they show you letters and say you what way you can read, and they tell you you have 10 on 10 or 8 on 10 or 6 on 10 or 1 on 10 vision. In fact, the real way to do it is to use either the Foucault's test, which is stripes, clear and dark stripes, or the Landau's test, which is circles open like a C, but you can orient different way. And why orient different way? In order to see if there are any spatial problems in your eye. And in fact, they show you this Foucault or Landau test at the same distance, and then they shrink the thing, and they tell you, now do you see the opening of the circle, or did you see the difference between the stripes? And from a moment that you say, no, I don't see anymore, then if you know the distance, you calculate the angle, and the visual acuity is the inverse of that angle expressed in minutes. Okay? And then they give you a value on tenths. 10 tenths is the best. And if you go down, you have problems, and this changes, of course, with the age, but that you have to know, 10 is not the highest value. There are people with more than 10 tenths of vision. And not only those people, they have best eyes than the average one, but today we know how to exercise people in order to keep vision highest than 10 on 10. This is cost a lot of money, and we use these techniques to train pilots for military aviation, because when you invest a couple of millions dollars to train a young pilot, you cannot say him now at 30 years, your visual acuity is going down, I cannot use you anymore. You have to have a return on the investment, and then the only thing is exercise special people to keep their vision as high as possible. That means for us, when we have myopia problem, unless to take glasses that cost not a lot of money, it could be possible to have some exercise to reduce the effect, but that costs a lot of money. Okay. Other thing, our eye is an optical system, but it's also moving, has moving parts. And in fact, the eye globe can move if you take into account also the contraction and the retraction of iris. You have 6 degrees of liberty, which is extraordinary. And in fact, we have 2 modes of eye motion. The first one is sequential. You scan in a given direction. And the second one, which is the natural one, is by jerks. The eye moves to almost arbitrary way and try to collect information all around the space. And this is the jerk motion is the natural one. When I am here and I look, my eye is moving, your eye is the same, but you are looking me, and when you are looking me, you focus on me, and if I move, you pass from jerk to sequential. What is the purpose to passing from one to the other? Look the screen. For a moment it's white, but look the screen. Now you are in jerk mode. You are saying where I have to look the screen. Most probably inside the red rectangular area. Look the screen, not radium. Now you have a line. And now you have a car. I see you. Once you locate the car, the jerks allows you to locate the car very rapidly. Then you fix it and you follow the car with a sequential motion. This is something which is very important for reading. The way that we read a sequence is linked to this possibility to switch from one mode on the other. If you take that text, that text works for people writing from the top to down, from left to right. If you go to other cultures, you have to inverse. And in fact, when you look this text, you see on the top they are small figures, numbers in red. This is the position of the eye. In fact, we learned that a text starts from the top and right, and you see 0 position of the eye is just in the word position. A small jerk, 2, 1, 1, 2, and you see that this word starts with a lowercase letter and ends with a point. Most probably, this is not a full sentence, is not interesting. Then you continue, you see ultimately, it's just after a point, starts with capital. This is the start of a sentence, and then you scan the sentence linearly, and you read the text, and also you avoid some Kabbalistic characters here that they don't have to do anything with the text. It's very funny. There are some visual traps that you can show you a text which is meaningless. Yeah, thank you. Is meaningless, but you can see a sentence inside because your brain make abstraction of any symbols that they don't have to do anything with the writing. No, it will not work with my computer. Okay, let's look a little bit closer the eye anatomy, and this is very interesting. Well, in fact, you have the pupil, you have the cornea. The color of the cornea depends on our genes, and women's they have more palette of colors than men's, and you will see also that ladies they have best vision of colors than men's. This is true, and you will understand why later. Then you have the crystalline. The crystalline is a lentil that changes the focal distance. You can go from infinity to 20 centimeters almost instantaneously. There is not any optical zoom able to do the same thing at the same distances. Okay, with just one lens. You need to add many lenses and have a very complex optical system to do the same thing that the eye does with a single length. Small problem when you are operate for cataract, they get out the lens, the crystalline, and they put a plastic one, and this one cannot change shape. That because after the cataract you see better the colors, but you need adaptive glasses to see as before. And at the end here, this is that we call the retina, which is all the different photoreceptors are here, and you have the central part here of the retina, which is straight in the entrance of your eye. This is the fovea, is the part that we see best, the colors and also the smaller size. And then you have the optical nerve coming back to the brain. Well, there is a cut here of the retina. Sorry. Continue. And in fact, the light is coming from here. And you see it penetrates different layers. I don't want you, of course, to know what is all those layers. They have different functionalities. I will explain you some of them. And then you arrive just before the white part of the eye, the sclera, which is the external part of the eye. You arrive here with a layer that they are the photodetectors, the cone and the rods, that they are sensitive to the light. That means light has to travel through few microns of retina before reaching the photodetectors. Well, and now if you take the eye and you cut it here and you develop it, you see that the cones, which is the more sensitive photodetectors, and they are characteristic of humans. The cones that we have here is only humans and also some big monkeys, gorilla, and also some others. They are concentrated in the central part of the eye. But the rods, which is less sensitive, and the rods, they're common to all living species with eyes, from fish to reptilians and humans. They are very older than cones. They are distributed more in the periphery of the eye. And as I will explain you a little bit later, the cones, they are less rapid than, the rods, they are less rapid than the cones. This explain the change of the visual field when you are moving with a given speed. And you have then a place here that we call the blind spot, which is the nerve In fact, I remind you that the cones and the rods, they are at the front of the eye and of the eye, just just before the external part, and then all the signal has to be collected by small nerves, and the nerves, they have to combine and go back to the eye. That means the nerve pass in the front of the eye and goes out, and the place that the nerve is coming out from the eye, there is no cones, there are no rods there. It's a completely blind spot. You can find that blind spot if you take a page, you make symmetrically two dots, two black dots, and you fold the paper, and then you start moving the paper in the front of your eyes without blinking the eyes or moving the eyes, and you will see at a moment the two spots will disappear. This is exactly where is located your blind spot. But when you are looking here, you are not seeing any black area. The brain behind smooth the image and correct the existence of blind spot. Okay, let's look the rods. There is a rod, and a cut of rod, don't go over that. There is a very large number. We have at around 125 million rods per eye, mainly located in the peripheral part. They are very sensitive. Two photons, or a single photon if you want, hitting a rod has 50% of chance to start the visual process. That means two photons arriving almost simultaneously to the rod, you have 100% of chance that the visual process starts. But they are slow in adaptation time. They are more adapted to the variation day-night, and not really adapted to something changely very rapidly, which is enough when you move normally, but it's not enough when you take your car, your train, or a plane. And they are colorblind. Okay? There is the response of the rods here, and this response can change as the quantity of light, available light change. When you are in daylight, they are working in photopic conditions here. When you are in a night, without moon, without any other source of light beyond the stars, they are working in scotopic mode. You see, you pass from yellow-green light here to more bluish light there. I will speak about that. And when you are in two light conditions, the response is between. Okay? The rods are sensitive to brightness. A rod reacts to a single photon. And here you see the yield is 50%. And in fact, our eye, what is striking is the brightness or the luminance, thanks to that, and more especially the variation, spatial or temporal variation of brightness. Well, when you are sitting somewhere and you are thinking, I don't know on what, and you still keep your eyes open, what happened? Sometimes everything disappears in the front of you, and you are thinking, you are in your world, this is fine, unless if something moves around you. If something moves around you, immediately you are looking, if it is not a leopard or a tiger, looking for you. It's a question of protection. And the rods can go down to 10⁻⁸ candela per square meters. I remember you, one candela is a candle. Here is 10⁻⁸ candelas per square meter. It's just extremely low. Yes, in fact, our eye can see from 10⁻⁸ candelas from square meter. This is the starry night, up to 10 to 11 candelas per square meter. This is a sunny day when you have snow or a white sand beach in the equator. You have a part that cones operating, a part that rods operating, and you pass from photopic to scotopic, passing through mesopic vision. But, in fact, we are able to see 19 order of magnitudes in log scale. There is no any camera sensor that can see a so large range of brightness. Our eye can do it, but our eye can do it by range of 3 orders of magnitude. How it works? If I enter that room, I need some time to adapt in the conditions here, and the first thing that my eye, thanks to a jerk movement, will look where is the brightest area. The brightest area is there, is the light sources, and somehow my brain identify what is the luminance level here, what is the brightness, and will fix, can see what is 1 order of magnitude above and 1 order of magnitude below. And all the remaining is no more visible. And you know that phenomenon. Look here, where you are inside a dark place and you look outside in very bright area, you don't see anymore what is inside the dark place. Or if you are walking out in a bright area during the day and you look from an open window, if the lights switch off inside the room, you don't see anything in the room. But if someone switches on the lights, then you equilibrate the brightness level and then you can see inside. Okay? I told you that we need an adaptation time. You have see here. In fact, this is the time that you need to stay in the darkness in order to leave enough time to your rods to be activated and send the information to the brain. And you can see if you are in very low light situation, you may need 20 or 30 minutes to be adapted in the darkness. But once you are here, you don't see any more colors because the cones are not operational. Only the rods works, and the rods, they are color blind. But you can see something moving, or you can see there is a hole nearby in your path and avoid it. Now, if you go back to a very bright situation, first of all, you will be glared, and you will need maybe 20 minutes again to be adapted in the new situation. If I take you from outside to a very dark room and I leave 30 minutes there, you will be able to see a sense somewhere in the more darkest area of the room. But when you enter, everything is black. This is also something that's very important for lighting design after. Understand how many times you need to pass from one situation to the other, and this can tell you that never have brightness contrast in a place, difference of brightness higher than 1000. If you exceed 1000, if that place is 1000 times less bright than behind, this place will be invisible for me. I will look always that area. And also, that I was telling from the beginning, when you pass from photopic conditions, when you have a lot of light, to scotopic conditions, you see that you switch from rods plus cones, especially the cones here, and you see that the maximum here is 683 lumen per watt, correspond to 555 nanometers. Why 555? For different reasons. First, the maximum emission of our star, the sun, is at 555, yellow-green. Second, Earth atmosphere has a local minimum for the absorption at 555. And third, look around you, all the trees are green. Green is denominating dominating color. If the trees are green, means that the leaves and the trees, they don't use green. They reject green, they use the blue and the red area of the spectrum. And we, humans, we are adapted to our environment. We see better that the place that we have the more light and the more light reflected from the surrounding areas. Now, if you go in a starry night, you see that our eyes, they are more sensitive than in full day. You can see better. We are more sensitive in the dark, and you see here in wavelengths that they are located around the blue area. And then you can ask why blue. I can understand the yellow-green, why blue? In fact, this is speculations. Some people say that it's, as we have the same rods than fish, than mollusk, like also different kind of animals, most probably the rods has been developed when human beings, they doesn't exist, but somewhere in the evolution, the human beings come from animals that was living in the water. And if you take the transmission of water for 1 meter thick layer of water, then you see that the sunlight, the maximum of the sunlight, will be located at this wavelength. And this is the idea, okay, we are coming from, I don't know what, amoebs, and they develop lighting somewhere under the water, and one day we came out and we became humans, and then we had this adaptation to our new environment. Once again, it is a speculation. And when you are between that and that, then you have both cones and rod operating. Then we have that we call the mesopic vision, and you see here how we can calculate the standardized V of lambda curve using those two and the brightness level that is around you. This formulation here was not standardized till 2011. And one of works of my team, we eliminate the city of Albi nearby Toulouse with color changing lamps, well, color temperature changing lamps, passing to more warm white to more cold white when the power decreases. And we saw that we can make energy economies. But the problem is, if you are not here, you don't have any measurement device calibrate for the situations between here and there, because these curves have not been standardized, and that means a lux meter or luminance meter cannot measure any more candelas per square meter or lux, but it measures vegetables and I don't know what. Okay, it's meaningless. And in 2000, we demonstrate that in 2001. We got for that the first prize of International Agrotechnics Committee Centenary Challenge. It was the first Centenary Challenge, and this initiates some standardization work at the end of 2011 that has been standardized. The two other plots here, this one has been standardized in around 1931 or something like that, and that one 1951. It's just, the standards here, they are much older. It has been standardized by the International Illuminating Commission, Commission Internationale de l'Éclairage, Commission International of Lighting, if you take in English the acronym. Yeah, and this is the way that you make the ponderation. Let's look now a little bit closer the cones. The cones is our characteristics. Other animals have also cones, but not the same than us. Humans, they have three kinds of cones. We'll discuss about that. The short one, that they are looking mainly in blue, they are responding in blue. The medium size, that they are responding mainly in green, and the smaller one, sorry, the large one, the big one that is responding mainly in red. In fact, when you see the width of the distribution is rather large, but we consider today that the human eye has three kinds of cones, one responding in red, one responding in green, and one responding in blue. That's because if you mix red, green, and blue with light, you can get white. I'm not speaking about paintings. It's completely different. I'm speaking about light. And the three primaries is red, green, and blue. Well, okay, the sensitivity here is about 100 times lower than a cone. You see that the V of lambda curve in photopic is much lower than the V of lambda in scotopic. The cones, they don't need, well, they are not operating where is very few light available. But they are 4 times faster than the cones. That's because continue to see in the central point of your vision where you are moving in high speed. They are subject of a progressive desensibilization. If you stay outside, in the beach, for example, or in a nice area, and you have publicity panels around you, if they use very bright colors, those colors, they will start to change to your perception, will be less and less bright, less and less visible. That's because never use bright pastel colors in that kind of situation, because very rapidly they will be completely invisible. And also green cones are more sensitive than red and blue. If you send 1 watt radiative power to the eye, if the 1 watt is green, it will be maybe 100 times brighter than 1 watt red or 1 watt blue. Well, this is a computer simulation. This is the photo of a bird, and this is what the L, the red cone see. This is what the M cone see, the green, and this is what the blue cone see. And finally, that your brain perceive is that one. Some interesting stuff here, very interesting. When you look the real central part of the eye, the fovea, that you have mainly the biggest number of cones. And I forgot to say we have 125 million rods. We have a few thousand cones per eye, is much lower. And when you look the central part, you have blue, green, red cones. But if you take the center of the eye, there are 0 blue cones. The real central part of the eye doesn't see blue. And that means if you have a very small detail in blue, real in the front of your eyes, it will become invisible. And the fact also that there are much less blue cones inside the fovea than the green and the red. The green, they are the more numerous. The limits between white and blue, they are flu. You cannot see the real limit between those two colors. This is very interesting when people are working with publicity and want to make messages and things like that, but also with people when they eliminate something, what kind of light you have to use in order to better explore the things. And this is also that I was telling, when we are in photopic, we have the cones working, they are predominant, you see the colors. When you are in starry night, only the rods working, you don't see any color, you see only gray. And when you are in between, well, the color are distorted till they disappear completely. And I will show you some other interesting effects. But what is the real process behind all that? When a photon hits either a rod or a cone, I will not make the difference now. What happened inside? Inside the rod or the cone, you have a molecule that we call rhodopsin. Not only there are different type of opsins, it's a molecule of this type here. And this molecule has two isomer situations. One is you have an angle here, and one is straight. It's the same molecule, but one is this side, and the other is here. And what happens if a photon hits the double link here, then you pass from that form, which is the normal one, to that one. And now imagine that the molecule is inside the photoreceptor. When the photon hits there, he is changed in form, and this change of form will trigger here a small electrical impulse. And this electrical impulse will be collected by small parts of the nerve and will send, after initial processing, to the brain. And what will happen? After a few time, the molecule will pass from that form spontaneously to that one, but this may take time, and this explains the desensibilization of the cones. This explains also the adaptation time. For the rods, we pass from here to here in situ. That means the molecule stay in this place. For the cones, the molecule will go out and will go to another kind of cells further in the retina. It will be repaired and will come back to take his initial place, and this may take more time. But remind, we have 125 million rods per eye, and each cone can respond to only receive 2 photons. You have a billion of photons hitting your retina at any second. That means you have almost all the rods and the cones responding simultaneously. Do you think that our brain is able to treat 125 million signals at any moment? We are not speaking even per second. Okay? The answer is not. I will give you more information after. Well, what will happen? Our retina will compress the image. Our retina is doing a natural ZPEG of the image. And how that works? If you have cones that they are one near to the other, each cone has 3 terminations. One termination is going to the central processing unit, and the 2 other terminations communicate with the nearby cones. And what happens if this one see a value of 100 of luminance, will send 80% to other signals that they make the summation, and he will send an inhibition signal to that one by telling me I see 100, you get out 10 from your value. That means we see also 100 and send 100 minus 10, and the other, which is in a lower level, we have a contrast here. What will happen? This one will tell him get out 2, and finally this send 88 value to the brain. And when you do that, this compression algorithm is very efficient, and the objective is to enhance the contrast. When you have a contrast here, 120, finally that you see is 80, 88. Here you see 8 and 10, or 16, 16. That means you amplify the difference between the bright and the dark area. And this is very important because it allows you to see the contours. And just try to look at this, don't move your eyes, try to focus in the center here. If you don't move your eyes, you have the impression to see here, just in the junction, a white line, a brighter line. This brighter line is difficult to see in the screen. You can see it better in a paper version. But this white line that you can see here just in the interface doesn't exist. It's the phenomenon of what you said, your eye accentuates the contrast to show you the limit between the bright area and the dark area. Just here. And let's have some fun. This is a painting from Salvador Dali. I don't know if you know him. He's a very special, he was, he's dead. And when you have his painting, the signature of Dali is you see always a lady, the face of a lady, you can see it here, which is just an illusion. And people say that was his wife, or I don't know who, I don't care. But I don't show you this table for that, this painting for that. I will show you because Dali mastered very well this idea. And there is something here. Anyone can see something there? No? If I make a zoom, still no. If I add few lines, and even if I turn it, you see there is a small dog, a Dalmatian. In fact, what Dali makes, he completely destroys the contours. And by destroying the contours, the eye cannot see anymore the object. But now you know that in this painting here, there is a dog there. And if one day you go to Dali Museum and you see this painting, and you have a friend with you, you tell, there is a dog there. Yes, because now you know it. If you don't know it, you never find the dog. And this is in fact the idea of camouflage. Okay? When you have the planes painted with different colors and lines, it's very funny because I didn't have time to transfer. I took a photo of a leopard in the zoo 2 days ago, and it's impossible to see the leopard in the ground because it's exactly the same problem. Well, if you destroy the contours, it becomes very difficult to see the object. And this is important to see the object. And you understand why. Here, I remind you that there is something, the eye gets the light, and the brain decide what is the object. And if I show you that, what is that? Who will tell me what is that? A police officer making helping the circulation, okay? But if you look, there is no any close line here. You see just the contour, and you say up, this is a police officer. Okay, there is some trap inside because we say the casket, the thing for the sound, and yeah, the sign here. If I change a little bit the lines, it will be more difficult to understand. But here, you identify very rapidly a police officer. Here, there is, was I telling, you have an aircraft, which is has camouflage flying over the trees, and if you look it from above, you don't really see it. You have to think about. I will replace that image with a leopard. It will be much better. But of course, here, if you have radars, the radars don't have that problem. But the human eye, yeah, it's explain why. And this is much more interesting. What is that? Bathrooms. Okay? If you show that signal, that sign, to any person, unless if you have some people coming from I don't know where in a place that never been in contact with our civilization, all people know what is that. We condensate an idea to a single pictogram. And we can show that pictogram to any form, you will always recognize it. And this is very important. This makes the difference between us and the other animals. You understand why. But let's say what happens at brain level. When you see here the flower, the information coming through the eye, a chemical reaction, electrical signal compress of the signal and so on, and then goes back to the optical cortex, passing through different kind of areas of the brain, and finally the brain will decide what I see here. In fact, the brain is trained to recognize very rapidly contours. That's because the eye helps the brain to see the contour. You need 25 milliseconds to recognize a contour. You need 400 milliseconds to recognize a color object. The color comes later to our species, and it is slower function. And finally, you need almost half second to recognize an object, to see, I see a red rose. Okay? Now, our brain is a very poor sequential computer. The process speed in sequential mode of our brains is just 16 bytes per second. This one is billion or trillion of bytes per second. Okay? But the brain is parallel processor, and this is the strongest part. Well, what happened? When you see, for example, the snake here, the snake is a potential danger for our species, and when the information pass from the eye, pass first of all by a central place in our brain that called the amygdala, which is nearby the central area, and the amygdala is part of the reptilian brain. Is something that is common to all species, and inside this amygdala, we know that they are coded some potential danger for the species. You see the snake, the contour parts by the amygdala compare with the potential danger and say, oops, snake, and gives automatically reflex order to your legs to make to turn and go to the other direction as fast as you can. If you are adult, you can control yourself and stay. But I have seen my daughter when she was 3-year-old in a countryside. She went behind the home plane, and I see Marie coming crying, snake, snake, snake. Where is the snake? I catch the Marie. Where was the snake? Somewhere there. It was big, small, yellow, green, red. No information. The only information was snake in front of you, run, and we don't discuss more. And this is very important. If you are in the front of a cobra, 125 seconds to recognize that it's a snake can save you the life, and you don't have to wait half second to say that it's a cobra. Okay? Because it can bite you before the half second. Let's continue. And in fact, to work rapidly, our brain is using parallel information, use different information from different sense, but also with the compression system of our eyes, it eliminates redundancy. In fact, it looks only for the real information, which is the innovation over the redundancy. If you look at the screen, the white part behind is not interesting, it's redundancy. These lines here are redundant. You don't look them anymore unless if they change. Same thing here. Well, if you want to increase this ratio, the way that you have is to condense the information. And this is why it makes the difference between humans and any other kind of animals. We are not only able to have ideas, but we are able to put those ideas in a piece of paper. And we start by putting hieroglyphs, glyphs, like also the bathroom sign. Then we transform that in letters or figures. I can read that one. People from Arabic countries can read that one. You are in India, you can read that one. I can read a little better that here, but well, this is not 3, I think it's 2. Well, okay. What happened here, the fact that we write symbols, that they are either words or syllabic, we can write to a condensed way our ideas. And this is linked to the capacity of our eye to extract rapidly and compress the image and extract the content. But, this can be problematic also. Look that one, and can try to tell me where are the black spots. In fact, the black spots is moving. There is not any black spot in the image. Everything in the crossing is white, but the compression algorithm between very dark, very light, and intermediate, each time that you focus someone, the eye thinks to see a black. This is just an illusion. Look that one, move a little. It's not a moving GIF. It's a fixed image. But if you move the head, you have the impression that the system is turning. There is no motion here in the image. And I will ask you a question here. How many triangles you see there? Let's go. How many? How many triangles? 0? Nah. He has the right question, the right answer. Yes, there are 0 triangles. The definition of a triangle is what? It's a geometrical figure with 3 closed lines. Do you see any closed line here? But you can say, yes, I see one triangle here. I see one triangle here. As you said me, this is a police officer. So except that here, you are completely wrong. You see just 3 angles and 3 Pac-Mans. But your brain see triangles, like the black spots here or the motion here. And that I will show you, sorry, is for 18 and above. What you see here? Okay, no comments. If I show that to a very young kid, before 3, after 3, forget it. You see the same thing than us. You know what? See a young kid, he see 9 dolphins. Where are the dolphins? I took a time to find the dolphins. There are. The nose, the tail. For a young kid, this figure that you see, you and me, doesn't have any meaning. But the kids see the dolphins. And they are 9. I took a time, I count them. But above a given age, you learn things and you interpret the image to a different way. Well, what about color? Now, I don't make the experiment here. If I take one by one and I tell you to read that sequence, and I take the time, you will say red, yellow, blue, green, red, red, yellow, blue, red, green, yellow, red, yellow. Less than 1 second. If I show you now that one, and I ask you to repeat the same sequence, red, yellow, blue, green, etc., the fact that I added the color, I add redundance. And if I add redundance, my brain needs some time more time to identify, and this push me to read slowly this sequence. And if I show you that, red, and you see yellow, I can tell you this is the more difficult to read, because you give not only redundant information, but contradictory information. Some people in publicity play with that. In France, we have a telephone provider, SFR, who has a publicity. The name of his offer is red, and they say you red is green because everything is well done and things like that, and they send you an image, a green screen with a word in the middle, red. And all people is looking where is the red, and this allows you to stay more time in the publicity and remind that publicity behind. Okay? What is then the information that colors bring to us? If I ask you what is that, you will tell me most probably plants. Okay? It's just green stuff. Now I add only the green, the yellow, the green and the blue information. Now you can tell me this is trees, because you can see behind the sky, and even you can see a little bit clouds here. That means I'm looking above. Is no more plants, it is trees. And if you add the full color, yum yum, there is something to eat. You can wait a half of second before identify something to eat. You will be not starving within a half second, but you cannot wait a half second in the front of a cobra. Okay, this is why the eye takes more time. And in fact, how the eye see the colors, they are just illusions. It's a sensation. Human beings, they have three cones, red, green, and blue. Other animals, they have different cones. Dogs, for example, they have only, they see only in yellow, in blue. They don't have the same cones as us. If you take cows, they don't have cones at all. If you take birds, they have 4 cones. If you take fishes, they can have up to 10 kind of cones. And in fact, when the light arrives to the apple here, a part of the light, especially the blue and the green, the blue and the green, they are absorbed by the apple, by the surface, and the apple reflects only the remaining part, the yellow and the red. This information go to the brain, and you see something is red, has the form of an apple, has the taste of an apple, the texture of an apple, and then you say in half a second, this is an apple, I can eat it. Usually, humans can distinguish at maximum 350,000 colors and shades. And that can be done mainly by women's. Men's, we can identify less, but then you can ask, my screen is displaying millions of colors. Why? In fact, we are not able to see millions of colors. But if you change a little bit the color pixel by pixel, then you make the image much smoother, and the result, you have a much more pleasant image. If you take all computers that you can change the number of colors, if you pass from million colors to 256 colors, and you have the same image, you see immediately the pixels. Only very few people have correct vision of colors. 5% of the world population is able to go so high, and it needs training. That means never try to discuss colors with the others. It's very personal stuff. And women are champions on that. I will explain you why. Because human beings, they have 3 cones. Ladies, 5% of the ladies, they may have 4 cones. They are quadrichromats. And the second cone can be nearby the green one, and you see here you may have an additional M cone or an additional L cone, never both, or no one knows about that. And that means if they have a second cone nearby the maximum of the eye response, they can see the color better than us. And that you see this assimilation between a trichromatic view and a quadrichromatic view. Okay? Ladies can see the color best. And this is well known also in the industry. If you take any industry that people working with color, always there is a lady who is working on the color sorting. Of course, then you can have color blindness problem. The most known is the daltonism, color blindness. You may have people that red cone is missing, that we call proton. That is the people that the green cone is missing, and this is the people with blue cone missing. And just look here. This is a photo that I made myself in Detroit, in the Museum of Cars. And if you are proton, you see that one. If you are deuteron, you see that one. And if you are triton, you see that one. And there is even, this is used to define the colors. In fact, what happens if one kind of cone is missing, for people, for example, that they don't have the green cone, this pink area here will appear exactly the same than the green area, because the two colors, they have the same response for the red and the blue cones, but the green cones who make the difference is missing. And look here, this is the Ishihara test. If you go to the doctor can say you that. Here, if you are normal vision, you see 8. If you are proton, you don't see anything. If you are deuteron or triton, you see different things. There are some other color blindness. We have people that they see only blue. And from that you pass to that. And very seldom you can have people that are completely achromats. They are looking like in all they are seen like in all the cinema movies at the beginning of the century, white and black. I have a few minutes then and we stop to make a break. People, they are trying since 19th century to understand how color vision it works. The first theory for color vision has been established by two physicists, Young and Helmholtz. They are very well known for different other effects. And Young and Helmholtz, they suppose that there are 3 independent photoreceptors, blue, green, and red. They make the right guess, but at that moment they didn't have any anatomic results. They didn't know exactly what is inside the eye. And they said, okay, when I have something red here, the red photoreceptor respond and the brain see red. If I have white, all respond and the brain sees white. It seems absolutely logic. Do we agree? Yeah, but I will show you a small experiment. And I will show you a figure. I will ask you to focus for a couple of seconds the black spot in the middle, and then I will change the image. Look that, please focus sometime the black spot without moving your eyes. 1, 2, 3. What we are seeing there. You see the same heart, but in the opposite colors. It was yellow and green, and if you focus and you will go back, you will see pink and blue, blue and pink, sorry. You will see the opposite colors. And this experiment has been done a few years after Young and Helmholtz theory, and they said if we have only one kind of, or three kind of cones which is independent, why the remanence image is in the opposite colors? That means that Young and Helmholtz theory is not working, and two other guys, Herring, and I don't remember the others, he proposed another theory, which is the conchular color theory, that said we don't have differentiate color receptors. The color receptors, they just see the quantity of light, but what happened behind differentiate colors. If I show green, then this one will activate red. This one will activate the red channel, and the brain see red. And if the red spot disappear, then this part of the eye will discharge, and I will see the opposite. I will see green instead of red. That explains the previous experiment. Problem is, this is 1867. A little bit later, beginning of 20th century, we had anatomic data that show there are three different kind of cones, like the previous theory, but the problem was still the same. And in fact, by looking closer, the reality is always much more complex. We have three different cones. We have rods, but in fact, the cones communicate between them. The red cones send information to the brain, and they send information to the other cones to inhibit the signal. And S cones, not only they are fewer in the retina, but they have only one termination. They don't interact with the others. And if you apply that model, you send red here, the brain says red, but when the red will disappear, then the green code, which is inhibited here, will send the green information for the remnant image to the brain. This is a mix between the two theories. And that was, yeah. Today we are able to write that in mathematics, and we can really reproduce the working of our brain. Okay, questions? Okay, if no questions, it's 11:30. I will suggest to make a break till 11:45, and then now you know how the eye working. We'll start speaking about the first technological component of the system, which is the lamps, light sources. And today, if you agree, I suggested to Pradium to have also a slot this afternoon from 3 to 4 to finish with the light sources, because I will speak about legacy light sources, fluorescent lamps and things like that. And I want to speak also today about LEDs. Tomorrow we'll speak about fixtures, drivers, and then we are ready to start thinking how to light up. Okay? Well, 15 minutes of break.